Here we have a short video discussing the Pythagorean Theorem. So what is the Pythagorean Theorem and what is it used for? First, it is used to find the missing sides of a right triangle. What does a right triangle look like? Here we have an illustration of it. We have a right triangle labeled with the box down the bottom left corner signifying we do have a right triangle, a 90 degree in the triangle with side lengths A, B, and C. Now sides A and B have names for them. Those are called legs of the triangle. So if they ask you what the legs are, these are the sides that are not directly opposite of the 90 degree angle. The side opposite of 90 degree is called the hypotenuse. C would be called the hypotenuse. And the formula for the Pythagorean theorem is a squared plus b squared is equal to c squared. So the sum of the two legs squared is equal to the hypotenuse squared. Let's use this formula to solve some problems. So first, let's find the value of x. We're going to round our answer to the nearest tenth. We have a simple problem here with both legs given to us. We have 8 as a side and 13 as one of the other legs, and the hypotenuse is x. We're going to use Pythagorean theorem to find what x is equal to. So first, let's use a squared plus b squared equal to c squared and plug in what we know. We know that a is equal to 8, b is equal to 13. So we plug in those values, and then we're just going to change c to x since x is the hypotenuse of the problem, and that 8 squared is 64, 13 squared is 169. Add up the 64 and 169, that gives us 233. That's what x squared is equal to, so all we need to do now is just simply square root both sides of the equation. And the square root of 233, we typed it into our calculator, do a little bit of rounding, and that tells us that x would be equal to 15.3. That would be the length of the hypotenuse for this particular triangle. Now, Pythagorean theorem problems will not always give you the hypotenuse as the variable defined. Maybe it could be one of the legs, which gives us in this problem. Also notice that this triangle is not orientated in our typical fashion where the 90 degrees is in the bottom left-hand corner. But if we just know that the hypotenuse is always directly opposite of the 90 degree angle, we can identify what our legs are. We have a leg of 7, we have a leg value of x, and that we can plug into the a squared plus b squared equal to c squared. So a would be 7 in this problem, x, my variable, would be the b for the problem, and the hypotenuse now is a value of 9. We're going to do 9 squared. Knowing that 7 squared is 49, keeping x squared as itself, and then simplifying 9 squared to 81, we can then simplify by subtracting 49 over to the right side, giving us x squared equal to 32, and like we did in the previous problem, by square rooting both sides, x would be equal to the square root of 32, or in other words, x is 5.7. Okay, other ways that we can see the Pythagorean theorem is that maybe there are two triangles embedded into one. If you notice here, there are two triangles that make up this one, where we have a smaller triangle and a bigger triangle. In this case, that the smaller triangle, we can label the base of it as the letter A, and the bigger triangle, we can label its base as B, giving us two separate triangles here. And we're going to use the Pythagorean theorem to solve for both of these and eventually figure out what the length of x is, what we have highlighted here for in green. So we'll start with the smaller triangle, giving us a squared plus b squared equal to c squared. Our b, in this case, is the 12, the height of this triangle, and the hypotenuse would be 14. Simplifying the squares, we have a squared plus 144 equal to 196, and then I can subtract 144 to the right side, and then square root both sides, and the square root of 52 would give us a decimal value of 7.2 when we round to the tenths. Now we move on to the bigger triangle. Let's do the Pythagorean theorem for it and find out what b is equal to, which gives us 12 squared plus b squared equal to 29 squared. Simplifying the squares, we have 144 plus b squared equal to 841. Subtract 144 over to the right side, gives us b squared equal to 697, and then finally square root both sides, which gives us a decimal value of 26.4. But that is not the final answer here. We know that x would be the sum of a and b together. Plug in those values of 7.2 and 26.4, gives us 33.6. So really the value for x, the length of x in the big triangle right above, is 33.6. We'll take a look at one more that has several triangles embedded into it, along with another geometric shape of a square. It tells us that the base of the triangle here, or the shape, is 40. but we need to figure out some lengths of other parts of this shape by saying, well, if the top of this square is 26, then we definitely know that the base of the square is 26, since the sides opposites are equivalent. And if we have 26 units of the 40, then we can figure out the lengths of the two sides of these smaller triangles that make up the side of this trapezoid. So they are both going to be the values of 7. Now that we have that, we could then go ahead and use Pythagorean theorem just to solve this triangle alone. One other thing that we notice is that we have symbols here that notice that the line on the right side tells us that the length of the diagonal is 20, which will tell us that the length of the other diagonal is 20. And therefore, we can go ahead and plug in everything we need for the Pythagorean theorem, which gives us 7 squared plus x squared equal to 20 squared, reducing down to 49 plus x squared equal to 400. Subtract the 49 over, giving us x squared equal to 351, and then finally square rooting both sides. The square root of 351 will give us 18.7, so the height of this trapezoid is just the value of 18.7. And of course, the last thing we would love to be able to do with the Pythagorean theorem is apply this to some real-world applications. So let's look at this example. A roofer leaned a ladder, a 16-foot ladder, up against the house. If the base of the ladder happens to be 5 feet away from the house, how high up on the house does this ladder reach? Well, it's a lot easier to do these problems if we create some type of illustration. So we're going to draw a shape here, a right triangle, and we're leaning the ladder up against the house, so that would signify this part of the triangle, or the hypotenuse. So that will tell us that the hypotenuse is 16 feet, giving us the base, since the bottom of the ladder is so far away from the house, that would be 5 feet, giving us a base value of 5. What we don't know is how high up or how tall the house really is. But now we got numbers and we got variables to represent what we need to know. Then we can go in and go straight to the Pythagorean theorem once again, and then plug in what we have and go ahead and solve. Using that Pythagorean theorem, we have a squared plus 5 squared equal to 16 squared, which gives us a squared plus 25 equal to 256. Subtract the 25 over. Subtract 25 over, and then we have a squared equal to 231. And lastly, square root both sides. The square root of 231 will give us a value of 15.2. So what this tells us is that leaning this 16-foot ladder up against the house would reach up to a height of 15.2 feet, as long as the base is 5 feet away from the house. And there's a short video over the uses of the Pythagorean theorem.